Okay, so what did you find? Did the distributive property work? Let's see here. So on the first one, doing order of operations, you have to add the two that are in the parentheses first and then do the multiplication. When you do that, there's the answer, negative 15, negative 8, 8, 7. Okay? On the second one here, you just multiply each of the products first and then add up your answer, order of operations. Okay, so the AB, I didn't have to do it again. I did it back on exercise 4, and then AC, it's being multiplied times the identity, so it's the same exact matrix. Okay, so then just add up those two numbers and take a look at the answer. Take at the previous answer. They're exactly the same, which means that the distributive property does work for matrix multiplication, which is handy. Okay, so here's a summary of some properties of matrices, properties of matrix multiplication. A, B, and C, they're just matrices, and K is a scalar, right? Just the number by itself that we can multiply. So you have an associative property of multiplication. It works, which means that if you're multiplying three matrices together, you can either multiply the second two first and then take that answer multiplied times the first one, keeping the order the same, or I can multiply the first two together, take that answer, and multiply times the third one. Okay? I have a left distributive property and a right distributive property. I have two separate properties for this, and the reason why I do is because, remember, if I multiply them in the opposite order, I get a different answer. Down there at the bottom, remember, there's no such thing as commutative property for matrix multiplication. Okay, and then also notice that you have an associative property for scalar multiplication as well, that if you have K, the scalar multiplied times the product AB, you can multiply the product first and then multiply times the scalar, or just multiply that scalar times A and then multiply them, the matrices together, or multiply it times B and then multiply them together. Notice that you don't multiply it times both A and B. If you did that, it would be multiplying K times K, which is K squared. It's a common mistake. All right? So there's a summary of some matrix properties. There's just a couple of more problems here to multiply, and that'll conclude this. So recall that multiplying by the number 1 gives you your number back. Okay? That is called the identity property of multiplication. In matrix multiplication, you also have an identity property. The identity matrix is usually denoted with a capital letter I. So notice that here is one of the few cases where commutative property does work. It's A times I or I times A. Remember, I is just the identity matrix, which is like the number 1. It gives you your matrix back, your original matrix of A. Okay? So a 2 by 2, well, actually, just in general, what an identity matrix looks like is for any n by n, it's got to be a square one. It doesn't work for rectangular ones. For square ones, you have 1s along the main diagonal and 0s everywhere else. So here's the 2 by 2 identity matrix, which we've already seen before. So 1s along the main diagonal, that's what I'm calling the main diagonal, and 0s everywhere else. So take a second here, and what do you think an identity matrix would look like for a 3 by 3? Obviously, it's going to be a 3 by 3 matrix, right? Okay, it's going to have 1s along the main diagonal and 0s everywhere else. It should be 1, 0, 0, 0, 1, 0, 0, 0, 1. Voila. So there is the identity matrix for a 3 by 3. Okay. Next question, find a squared. Well, what does a squared mean again? It means a times itself. So if I'm going to square a matrix, what I need to do is I just need to multiply that matrix times itself again. Negative 2, 1, negative 8, 4. So go ahead and pause the video here, multiply those two matrices together, and see what you get. Alright, let's see if this is what you came up with here. So the final answer should be negative 4, 2, negative 16, 8. So trying to make some connections to see if anything is true. Is a squared the same thing as all the entries inside the original matrix squared? Negative 2 squared would be 4, but I got a negative 4. Okay, so that's not true. Obviously not true. Is there some kind of shortcut, like squaring a matrix? If you look at those numbers, maybe you see something. Maybe you notice something about these numbers, the original ones, and the answer. Question is seeing one example play out enough to say that that pattern is necessarily true? Of course it isn't. But you're going to get a few more examples to check that out, maybe in the challenge problems or something like that, I think. All right, so final example. How about multiplying, doing the same thing, a squared, which means multiplying the matrix by itself, right? We'll just go ahead and do this one together. So 2, 5, negative 1, 4, 3, negative 7. Now, for a while here, we haven't been looking at the dimensions because they've all been square. Whenever you multiply square by square, it stays the same. Here, this one is, let's see, we got a 3 by 2, and I'm multiplying it by another 3 by 2. And, oh no, look at that. The number of columns in the first one does not match up with the number of rows in the second one, which means that you can't do this. Can't do it. Which is strange, right? You're used to being able to square anything you want, but here, matrices you can't square. What are the only kind of matrices that you can square? I wonder what those things are called. Anyway, so that concludes our lesson on multiplying matrices. Take a look at the pictures here. What do you have right underneath the objectives? You have some remote controls, RC, row times a column. And over here on the right-hand side, you have a very interesting looking roller coaster. It's going into the water? That's crazy. Roller coaster, RC, row times a column, because that is how we multiply matrices. You take a row, multiply times a column, and you add up the entries. All right, so there's your assignment, and of course we'll come together. See you in class.